My dear students, in the last class we discussed the definition of quotient group and some examples. In this class we also discuss some examples and the properties of a quotient group. So let us start with the example. For n greater than 1, z under addition and nz this is nothing but is equal to, we can say that the this quotient group this is the same as a we have a addition modulo nzn. So let us try to show that this is the quotient group of this z under addition over the g is equal to, we have take this is a set of integers, and then we have to taking this h is equal to, we have to take a n of z, and now this is clearly you can just check verify that this is equal to n is a normal in g. So we have to show that into this form. So let's a typical cosets of a n plus a we have a this is h plus a is nothing but the form of you have a because h is equal to nz, so you have a nz plus I types, where I is rise between 0 and n, and this is nothing but is equal to is coming to the z of n. So nza you just said that nzi, and you take a n is I is equal to 1, so nz n of z simply you have a n of z, you have take a, if any element of a z is 1, so 0 plus h you have getting into the same thing, and similarly into this. Now because the operation in this case is addition, so we write as a nz plus a and plus nz plus b, and this by the quotient group we can say that simply because g by n is equal to, we have a n of a, and then binary operation we have to define n of a plus this is because we have a under addition, so this is you can n plus a plus n plus b is the right cosets of this, then this is n plus a plus b. It's right into this form. So we just say that nz plus a and this nz plus b, and this can be written as a, by the definition, n h is equal to n is equal to nz and plus a plus b, and this a plus b is nothing but is equal to, which exactly the addition into the zn, and consequently this and this n are the same. So we can simply say that the z under addition over quotient group of nz is nothing but is equal to the same as a z of n under addition modulo n groups there. So this is clear. Now next example we have to taking, let g be a set of integer and h n is equal to, we have to taking as a subgroup generated by 5, and then this is nothing but is equal to be generated by 5n, and then we can easily verify that this n is a normal because you take any element of a g for and then again you take a 2 plus you can just take any element 2 plus any element of a z, then we can say that g and g inverse is equal to, we can say that g and g inverse is also the n, or we can, because is a binary operation is addition, so g we can take a 2 inverse of a 2 minus 2, and then we take any element of a n, so 0 plus 2 minus 2 is equal to 0. So all of them then can we can easily show that this satisfy this condition. So this means clearly we can show that n is a normal in G. If n is a normal in G, then we find the quotient group by this. And now we, because n is equal to, we have a 0, plus minus 5, plus minus 10, plus minus 15, and so on. So we have to find the what types the elements of a this. Let a be any element of this set Z. By the division algorithm, we can write a can be written as a, because it's a multiple of a 5, all the elements a plus 5, b plus c, where this C lies between 0 to 5, is generated by 5. So this can be written as a minus 5 is equal to a minus C is equal to 5b. And now you see this a1 minus 5b and 5b is the element of a for any b. So b and b are the for any integer a and b. So clearly this b is the element of a 5b is the member of this n. So this means 5b is the element of n. If 5b is the element of n, then we can say that a minus c is also the element of n. And then in the coset, we know that from this h is the element of h if and only if we have a h. So by this we can say that n of plus a minus c is equal to n. And now by the this we can say that n plus a is the same as n plus c. So we can say that this means if n minus c is the element of n, then this can be written n plus of a, and that is because c is the element of a lies between 0 to 5. So we can say that n plus a is the same as a, because c is equal to 0, so n plus a is equal to, you have a write into this form, and so on. So this is c is equal to 0, 1, 2, 3, 4. So n plus 0, n plus 1, n plus 2, n plus 3, or n plus 4. So therefore z over the generated by 5 is the element of a this is the element of the set of this quotient group of G by generated by 5, and then we can this table Z5 has precisely the same group as a under modification modulo 5, because we have to show that if Z, and then any subgroup of nz is also in the form of a Zn. So this is the special case of the previous example where we have to show that. So clearly we have to show that this table that under addition mode of under addition, then we have to taking this this is working as a identity. N plus 0 is nothing but is identity of this group, and then we have to, all the elements are here. We can just check into this form. We take identity element. Now they check this is n plus 1 as the inverse of n plus 4. You can just take a n plus 1, and then you just take a like this. You can say that if by the definition, I just write this, I just write in this form. We have n plus 1 n plus 4, and that is modulo 5. This can be written as by the definition n plus 4 plus 1, and then 4 plus 1 is equal to, you have a 5, remainder is 0, and that is equal to, we have to say that n. So one of the coset is equal to n plus 0, then we have to simply this. Now we have to check this simply n plus 2 plus the 3 is again. So we have a n plus 2 and plus n plus 3. So by the definition n plus 2 plus 3 under addition modulo 5. So this is nothing but is equal to n plus 0. So inverse of it n plus 2 n plus 3, and then similarly we have to just say that this is nothing but is equal to, as a simple similar table of this, you have a 1 2 0 1 2 3 4, and this is all the property of the same as a, we have a Z5. So this satisfies all the properties of a Z5. So this clearly we can say that this the quotient group, this Z over generated by 5 is the same as a Z5, and that is equal to same as a under addition modulo 5. This is the complete table of this representing of the quotient group of the this we can find easily the quotient group of a Z by normal subgroup generated by the 5. Okay, so now we have to discuss the converse of a Lagrange's theorem, and then show that there does not exist any group of order 6 in the A4. The quotient group can be used to show that the A4 has a no group of order 4, and then the converse of a Lagrange theorem is false in general. To see, assume that n is a, we have to assuming that n is a subgroup of a A4 of order 6. So we have to just say that n is a subgroup of a this n, assuming this is order 6. But you know that the index of this n and this is equal to, clearly is equal to, we have a g over n, and g is equal to, you have a 12 upon 6 is equal to 2. This is equal to 2. So index of a, this is equal to 2. Therefore, if any group is a we clearly assuming that n is a subgroup of A4, and assuming that this group has a order 6. If this group has a order 6, then the by the index of this n is with g is equal to 2. If n and g is equal to 2, then we can say that every group whose index is equal to 2 is a normal in G. So this means clearly we can say that this n is normal in G. So the condition is satisfied. This our result for a quotient group, n should be a normal into G is equal to, we have A4. And then by the theorem we can say that A4 upon n make a sense. So this means we have to just say that we have to first is define. So A4 by quotient group of this A4 n make a sense. And now for each A is the element of a n, then NA inverse is equal to NA. So NA for each A is the element of A and A ka inverse is equal to same as A, and because index is equal to, and A square is also n, so that n A square is equal to, we have a n, and so n A square means we can say that n of A into A, this can be written as NA, we have NA, and this is nothing but is equal to, we can say that n of A ka square, and n A ka square is there, then this is equal to, you have identity is nothing but is equal to n. So this means n A square, we can say that n A square, we can easily say that is equal to the n, and A square is the element of A square is the element of a n. So we just say that one can show that we can, by this we take a square of a 1 2 3, that is equal to 1 3 2. We can just take a 1 2 3, then we have a 1 2 3, and then you can just check is equal to 1 goes to 2, and then 2 goes to 3, then you have a 3 goes to 1, and 1 goes to, you have a 2, 2 goes to 3, 3 goes to 1. So you have a, this is clearly 1 3 2, and then similarly if you take a 1 3 2 1 3 2, then clearly say that 1 goes to 3, so 3 goes to 2, 1 goes to 2, then 2 goes to 1, and 1 goes to, you have a 3, and then 3 again goes to 1. So this means we can say that this is equal to 1 to 3 is equal to this form. And now we have a 1 to 4 and 1 to 4. Now we have to calculate 1 to 4. So 1 goes to 2, 2 goes to 4, 4 goes to 1, 1 goes to 2, and then we have a, again is going to 1. So this is a 1 4 2, and similarly if we take a square of a 1 4 2, we have a 1 4 2. Now we have a 1 goes to 4, 4 goes to 2, 2 goes to 1, 1 goes to 4, and then we have a 1 to 4. Similarly we have to calculate the 1 3 4 and 1 3 4, and now you have a clearly 1 goes to 3, 3 goes to 4, 4 goes to 1, 1 goes to 3, and 3 goes to 1. This is 1 4 3, and then if you take a 1 4 3, then you have a 1 4 3, then you have 1 goes to 4, 4 goes to 3, 3 goes to 1, 1 goes to 4, and then again 1. So this is equal to 1 3 4. Similarly we calculate the 2 3 4, and then 2 3 4, then you have a 2 goes to 3, and 3 goes to 4, 4 goes to 2, 2 goes to 3, then 2 4 3, and similarly for a 2 4 3, 2 4 3, we getting is the for 2 goes to 4, 4 goes to 3, 3 goes to 2, then 2 goes to 4, and then this is equal to 2 3. Now this lead that there is a 6 1 2 3 4, and then we have only 1 2 3 4, and this is the more than 6 different elements of a A4. So 1, 2, 3, 4, 5, 6, 7, 8 in A4, and note that, and this means size of n should be greater than or equal to 6. A contradiction, because in our assumption we have to assuming that the size of n is equal to 6. This means A4 has a no subgroup of order 6 by using this quotient also. So by this method we can also prove the converse of a Lagrange's theorem is not true in general. That means we have to taking by this we have to first take a assume that there exists a subgroup of n of order 6, and then we take a index of this with g is equal to 2, and is clearly n is a subgroup of this, then we have to index is equal to with g is equal to 2. So this is a clearly is a normal subgroup, and it is a normal subgroup, then we have to use the property of the quotient group, how to define, and then we have to show that there is a 6 different elements A4 in n. So that means order of n must be greater than 6, which is a contradiction of our assumption that order of n is equal to 6. So A4 has a no group of a order 6. This can conclude the converse of a Lagrange's theorem is not true in general. So let another we have to just try to find this. Let G be a group generated by G, and order of a G is equal to 12, and we try to find out the what is the quotient groups, elements of this quotient group. And let n is equal to generated by G to the power 4, then clearly if because you have a G is generated by order 12, and then if it is G and order of this is equal to 12, this means the element of this G is equal to, you have a identity, just we write into this form, we have element of a G is the form of a G square, G to the power 3, and so on, G to the power 12 is equal to identity. So this is the 12 orders. Then we have take a elements of a generated by this 4. So this is the n is the element of the form generated by G to the power 4, G to the power 4, G to the power 8, and G to the power 12 is equal to identity. So this means n is equal to, you have a identity, and then you have a G to the power 4 and G to the power 8 are the this. So if n is the element of a, you have a n is the element of this form, then we have to calculate the n of g. N of g, we have a g to the power 5 and g to the power 9. If we take n of g square, if n of g square, g to the power 6, g to the power 10, and cube if we take is the form of a g to the power 3, 7, and g to the power 11. And now if you take we have a n of g to the power 3, and you know that this is nothing but is equal to, you have a n of g into g to the power 3 is equal to n of g to the power 4, and this g to the power 4 is the member of n, and then is the member of a n. This means this is complete in the n, and this if this is the complete in the n, so we can say that we have a simply is equal to this is equal to in this form. So g and g this is a complete element of n. Thus this means we have a g to the power 4 belongs to n. Then this implies that we can say that n of g to the power 4 is equal to n. So by this we can say that so this is nothing but is equal to, we have to just say that into this form, and then you have to write this is nothing but is equal to n. So since this using this property, we have to g to the power 4 is equal to n, is n by the is property of a coset. We can say that n g to the power 4 is equal to n, and then clearly this is it. Now similarly we have to calculating this again we have to write in the form of this n of g 2 square and n of g to the power 3 by the property n of g to the power 5, and now n of g to the power 5 n of g to the power 5 belongs to the n of g, and then you have a g to the power 5 belongs to n of g, and then this means written as n of g to the power 5 is equal to, you have a n of g. So this means this n of g to the power 5 can be written as a ng, and then since g to the power 5 belongs to the ng, so g to the power ng, this means n of g to the power 5 can be written in the form of a ng. And this means we have to write in the similar fashion, we have to write all the elements of the different right cosets of this in the form of a n, and then ng square, and g to the power 3. No other element into this. This is working as an identity element. This is working as identity element. And now you see this, we have to just say that inverse of this is equal to, clearly by this, ng into n of g cube is equal to n of g to the power 4. And now we have to show that this is equal to n by the using the property, since g to the power 4 is equal to is the member of n. So this means this is clearly, this is the complete group table of this. If we have a g to the power group is generated by g is a group of generated by g of order 12, and normal subgroup is generated by g to the power 4, then g by n, element of a g by n is equal to, clearly g by n, the member of this is n, and g, n of g square, and n of g to the power 3, and they are form a clearly this scalar table say that this clearly form a group under the operation of a cosets we have to define for a quotient group. Okay, so now we have to explore some properties of a quotient group. First one is, we have to just say that let G be a group and n is a normal subgroup. If G is abelian, then G by n is abelian. So this means we have to, if G is a group and n is a, we have a group, G is a group and n is clearly have a group is a normal subgroup. If G is abelian, so G is abelian means we have a AB is equal to, we have a BA is given, then we have to show that G by n is abelian. G by n is abelian. We have to take any two elements of this, suppose x and y is the element of a G by n, and then if x is the element of a G by n, then this can be written as a n of x, and then y is the element of a G by n, then this is nothing but is the element of a n y types. So we just try to show that nx x and y are the element of a 2g and y. Then we have to show that x and y is the same as a y of x. So now let us begin with this, because we have to taking the n is a normal subgroup. So we just try to Na and B are the element of a 2Ga. So we just take a two elements Na and B, because I just take or take x and y are the element of a G by n. Then x can be written as a n A types and y can be written as a some n B times. And now if we take a x and y is nothing but is equal to n A and B. This can be written as n of by the property of AB. And now A and B are the element of a, we have A and B are the element of a G. For all AB are the element of a G. And if for all A and B are the element of a AB are the element of a G, and G is, you have a abelian. So this implies that AB is equal to BA, and this means this can be written as n of BA, and then again we have a NB, we have NA, NB is equal to, we have a Y, and this is NB is equal to X. So ultimately we have to show that if X and Y are the element of a G by N, then this implies that X and Y is equal to Y of X. So we can say that if so we can say that if we have G is a G be a group and N is a normal subgroup. If G is abelian, then G by N is abelian. So this is proof is very trivial. It's not very difficult. So we have to just now very interesting thing. What about the converse? If G by N and abelian, it is possible that G is abelian. So this is naturally we have to ask a question, if G is a group and is a normal subgroup and G by N is an abelian, is possible that G is a group? The converse is not true in general. Now we have to provide an example. The converse of the above theorem need not be true in general. So let G by N is abelian, and then G may not be abelian. So we have to show that say G G by N is abelian, but G may not be abelian. So I take a non-abelian groups. For example, I take a G is equal to, you have a S3. And if you take S3, you know that the S3 element of S3 is equal to identity. You have a 1, 2, and then you have a 1, 3, then you have a 2, 3, 1, 2, 3, 1, 3, 2. And this is the group. Is clearly you know that this S3 is a non-abelian group. Now we just show that this means there exists an group of normal subgroup. We have to take N is equal to, we take a identity 1, 2, 3, 1, 1, 2, 3, and we have a 1, 3, 2, and now this you can check easily. You have a clearly this N is a, we have to show in the last class, N is a normal in G. And now if N is a normal in G, then we have to calculate the cosets of this G by N. That means we have to write is equal to, just write into this form. So N is equal to, I take this form, then G is a non-abelian group, N is a normal subgroup of a G, so we have to write into this form. Because you know that the order of the factor group is order of a G is equal to 2, and then if order of a Gn is equal to 2, this every group of a prime order is cyclic and so is abelian. So this means order of a G is equal to 2, so this means G by N is equal to order 2. Every group of a prime order is cyclic, and then and it is abelian. So this means we can say that G by N order is equal to 2 and G by N is abelian. So we have to find that the G by N is abelian, but there exists a non-abelian group where N is the satisfy into this form. You can easily verify this N is a normal, because you take any element of this, you have to take a 1, 2, and then we take a N and 1, 2 inverse. You know that 1, 2 inverse is equal to, I just take it in this form. You know that the inverse of a 1, 2 is equal to 1. So we know that 1, 2 inverse is equal to 1, 2. I take element of a 1, 2, and then we have a any element of a this is equal to 1, 2, 3, then 1, 2. Now just see this is similarly is equal to this is 1 goes to 2, 2 goes to 3, 3 goes to 3, and then again you have a 3 goes to 3, 3 goes to 1, 1 goes to 2. Then you have a again 2 goes to 1, 1 goes to 2, 2 goes to 1. So this is means you have a getting this is equal to 1, 3, 2, and 1, 3, 2 is the member of this set N. So this means clearly 1, 2, 3 with the 1, 2, 3 is equal to the member of this. So this means clearly all other properties satisfy this condition. Then clearly this N is a normal subgroup of this quotient group, and by other method you can also say that we have to just say that G3 by N, and if order is equal to 2, and then we have a index is equal to 2, and then means it's a only this two different cosets are there. So this means we can simply say that we find a example where G by N is abelian, but G original group G is not abelian. So we just means if we have and G is a group and N is a normal subgroup of a G, G is abelian, then G by N is abelian. But if G is abelian, then G by N is abelian. But G by N G may be a non-abelian group. There also exists a G by N as an quotient abelian quotient group is there. So this means we can there prove the converse of the that theorem is not true in general. So just I just to stop today's lecture up to this property, and now in the next class we continue to some more properties of a this quotient group, and and try to solve some of the problem related to this quotient group, and then we have to solve other. So thank you very much.